Hi, this is Jeff from the Ozark Mountains in Missouri, USA. This is the third part of the series about converting a Commodore 64 into a CNC controller. Today is an update on the software, and we're actually making a motor spin. I like to call it counting cycles and cycling motors. A lot of the thrust of the last week or so has been put into optimizing the code running on the Commodore 64, particularly the code in the interrupt handler for the non-maskable interrupt. Since it runs 1,000 times per second, every cycle in there really counts. It gets multiplied by 1,000. There was also a small change made to our step pulse generator board. We'll go into that in detail in a little bit. And finally, we hooked our step pulse generator board up to a Gecko stepper drive, and we make a motor spin around and then back around to where it started from. So let's jump in and take a look. The G-code parsers had just a few improvements. It now outputs the correct direction bit mask in all cases, and it outputs a mode setting that tells the interpolator which axis is being interpolated over. In other words, if the delta X or delta Y is greater. So now we can generate the correct code for all 8 octants. Let's take a look at that. Here is our slightly improved BitBasher. I've added a mode column here and removed a couple of the columns to make the display a little less busy. The big advantage now is it correctly sets the mask and gives me the mode so it can generate settings for all 8 octants. In other words, no matter if the X or Y are positive or negative, or if the slope is greater than 1 or not, it'll generate the correct output. So here we have X of 512 and 128. So this is in the quadrant 1, and X is changing greater than Y. And this is the output that we get. So we have no direction bit set, and it's in mode 1. And if we change this to say minus 512, it sets the mask correctly, so it'll reverse the x-axis. Now if the delta Y is greater, notice it sets it to mode 2, and instead of dx and dy now, for the delta x and delta y, we have delta A and delta B. So delta A is the axis that has the greater change, and delta B is the other axis. And in the interpolator code, it looks for this mode setting to know how it should interpret what these columns are. That gives us one simple main loop instead of multiple main loops. Most of the work this past week or so has been on the Commodore 64 side of things. What I've done is trim down the code to save a lot of time and some space, although I'm optimizing for runtime, not code size. And part of that is using macros in some places instead of subroutines to save a little time. And I've incorporated the 2 additional bytes that the BitBasher is giving us. And with all these changes, we can generate 9 to 10 bytes of output data between the non-maskable interrupt calls. So let's have a look at those changes. Here are the sections of the Commodore 64 code that were changed in the interpolator section. We incorporated in that mode setting. So what this does is, for instance, if we're iterating over the x-axis because our delta x is larger, then we're associating the x step bit with the A column and the y step bit with the B column. And if we're iterating over y instead, then we do the opposite. And you'll see some things that I've commented out like this. Some of those I'll point out are things I took out to save a little time, and others are things that I've tried, and I'll try to point out what those are as we go. For instance, on these 2 lines right here, this compare to 0 is not needed, because once we load y with this, the 0 flag is going to be set if it's 0, so we don't need those lines in there. This is a different way of doing the code that's right below this that didn't work out. Something's happening when it goes through this top section from doing the 2 exclusive ORs in a row that's messing things up, and I just haven't figured it out yet. But if I can get this figured out, it'll save a few cycles on all the paths, or the Y step, or the B step actually. The minor axis is being stepped. It'll save a few cycles then. And so here's the code that corresponds with this. This is actually the working code here. So if we need to step the Y, or the minor axis, if you will, we do that here. And of course, we're stepping the major axis each time. And instead of doing a jump subroutine to out buffer right, we're using it as a macro, which saves a little bit of time. And this is just a testing thing here. I think you saw that last time, where we're counting the number of bytes we output. So if we look at that output right as a macro now, right here, this is basically what it looked like last time. We got rid of, it went from 33 cycles to 26 cycles, mostly because we're got rid of 6 of those because we're using it as a macro. Actually, I think this should be 27 cycles, so the savings is all from the macro. I tried a few different things and settled on this because it works, and I can keep a consistent output between all these macros. One other thing that made a sizable difference was moving all of the most commonly used variables, aka memory locations, moving all those I could to 0 page. So what I did is I went through the main loop and I made a list of all these things that I was using, like the x index, y index, fractional high and low, things like that, and which were used the most. And I, by that order, assigned them all locations in 0 page that were free. And I started out with all the sections of 0 page that are used for tape loading, which I'm not going to be loading anything from tape while trying to use this as a CNC controller, so this worked out pretty well. The changes made in the interpolator and here in the pulse engine, which we're getting into, allowed us to go from being able to create 4 to 5, maybe 6 bytes for every byte we output, to now we're about 9 or 10 bytes for every byte that we output. So we can kind of work ahead a little bit and get some stuff stored in the output buffer with ease without fear of running out. Now let's look specifically at the changes that were made in the pulse engine. Now on the pulse engine, this was the biggie here as far as saving time. The reason is this is running at 1,000 times per second. So any clock cycle that's consumed here is multiplied by 1,000 every second. So if you save 10 clock cycles in the pulse engine, you're saving 10,000 clock cycles per second, which is a lot considering there's only about 1 million of them per second. So this is about as bare bones as I can make it. I did add in saving the status register here, which I didn't have before, which caused problems. So we're saving all the registers, clearing the interrupt. We're doing the reading from the out buffer as a macro. We skip writing if there was actually nothing to read, and then we restore all the registers. And if we look at this out buffer read here, this is what it looked like before. It was about 33 cycles, and that's been trimmed down to 22 by using a macro and simplifying it quite a bit. And luckily this works, because we saved almost, we saved about 11 cycles there, so that's 11,000 clock cycles a second. Let's say average instruction length is 4, so we've bought ourselves maybe 2,000, 2,500 more instructions that we can execute every second. So this was a significant change. When I went to wire up a stepper drive, the one thing I hadn't considered before was the settle time needed on the direction line before a step pulse is received. So the stepper drive needs to make sure that all its internal circuitry is situated before it receives a step pulse. So anytime you change the direction line state from low to high or high to low, you need to have at least 250 nanoseconds before the next step pulse is received. And this could have been done in the pulse engine code, but that would have taken a lot of clock cycles, which we know isn't a good thing. So what I did was switch the outputs from the 74123s from the Q outputs to the not Q, which are inverting outputs, and I changed from OR gates to AND gates. So the effect is that we get a negative going pulse that are ANDed together, so it's kind of like an inverted version of what we had before. Here is my hand modified schematic. So we're taking the outputs from the Q output to the not Q. So instead of getting a positive going pulse, we get a negative going pulse. And instead of ORing them together, we're ANDing them together. And the result is that we get a negative going pulse on each edge of the signal. Now the stepper drive steps on the rising edge of the signal. So we'll look at the scope trace here in a minute and see how that actually works, but this solved the problem very nicely for us without requiring additional hardware or lots of more slow code. Here we've got an oscilloscope capture of what's going on with our modified step pulse board. The bottom blue trace is our direction line, and the top yellow trace is the step line. You can see the step line is going from high to low and back to high, and remember that our stepper drive steps when the signal goes from low to high. As our direction line goes low, the step line also changes from high to low, but the stepper drive doesn't care about that. It steps when it goes from high to low, which is about 18 microseconds later, which gives us plenty of time for the settle time that the stepper drive needs. Here is a quick shot of the overall test setup. So we've got our Commodore 64 in the monitor, and now in the center of the screen is our pulse board, and we see the oscilloscope there, and finally we come over to the stepper motor, a stepper drive, and a 24-volt power supply. Here we have our stepper motor. This is a NEMA 23 276 ounce-inch motor that draws about 2.8 amps. Next we have our stepper drive. This is a pre-production Gecko GM215. I'm using it in stepper driver mode, not motion controller mode, and it is set to 1/2 step input. And here's our modified step pulse board with the AND gate instead of the OR gate, and we've got the scope probe set up to monitor the step and direction line for the x-axis. There was a lot of background noise, so I'm going to cut in some voiceover with some sound recorded at the actual time, so bear with me. Now let's have a look at the scope trace of the signal. You notice there is a lot of noise here that's being fed back from the stepper drive, so we're going to have to take care of that. Now if we go ahead and run it, the top yellow trace is the step signal and the bottom is the direction. Now you see the direction change as the motor reverses. I hooked my signal generator up to the stepper drive with a 1 kilohertz square wave, and it was just as noisy. And I read the manual a little more, and I remembered that there are a few pots on here to tune for smoothness with low speed signals. So I did that, and it quieted down quite a lot. I'll cut in some actual audio now. RPM. So that is what I did there, and as you can see, that is much less rough. So where are we at now? Well, our updated pulse generation board works, and we can interpolate in all 8 octants and use a fairly simple main loop while doing that. We're still only 2D, X and Y. We'll add in Z later, and there's still no acceleration or deceleration. For short-term goals, I really need to figure out how to add in the acceleration and deceleration as well as an actual velocity setting, and to add some better isolation between the pulse board and the stepper drives. The long-term goals haven't changed from the last update. We still need to improve the G-code parser, have a simple user interface on the C64, be able to dynamically load Commodore code files, and maybe do that even while it's running. Well, I hope you've enjoyed this look into the CNC controller made from Commodore 64. There is more coming up in the future. The next video or two will probably be about Commodore 64 repairs. I've got one coming up on case repair, as well as a nice black screen repair. I'm just waiting for parts for those to get them done. Also, take a look down below at the subscribe button. Just click on that guy. That way you'll know when I post a new video. And if you click on the bell icon, YouTube will be sure to notify you right away when a new video is posted. I sure would appreciate it. Thanks. Until next time.